Experimental design involves setting out a clear plan for data collection and analysis so that your conclusions are objective and sound. When planning your experiment, you need to define the experimental units and response variables, specify the treatments and how they'll be given, identify the controllable and uncontrollable variables, choose a design, and work out how many replicates are needed. One of the most important considerations of an experiment is how to even out the variability among the experimental units to make comparisons between the treatments fair and precise. For example, if you are testing a new manufacturing process at your factory by measuring levels of employee productivity, you might reasonably expect Monday production levels to be higher than Friday productivity when employees' thoughts turn to going home for the weekend. You could randomly select which manufacturing process to use each day, old or new, for several weeks. However, day of the week is a source of variability that you should control for. One solution to the problem of potential variability is to use blocking. Blocking involves putting your experimental units into groups based on something they have in common, so that units within the groups are as alike as possible. Then, you randomize your treatments to the experimental units within each block. So, for our manufacturing example, we might block by day of the week. The dates over which the trial is to be run are assigned to blocks based on day of the week. Then, within each block, the dates are randomly assigned to either the old or new manufacturing process. Any resulting production increase or decrease between the dates can then be more confidently attributed to the manufacturing process used. Let's explore the concept of blocking using an example. A randomized complete block design is a commonly used experimental design in which the experimental units are grouped into homogeneous blocks. Each block has the same number of experimental units, usually one for each treatment. Within each block, the treatments are randomly allocated to the experimental units so that each treatment occurs in each block the same number of times. An experiment is being devised to investigate the effects of different flower foods on the longevity of flowers, that is, how many days flowers last in full bloom before wilting. The experimental units are 24 plant trays, each containing either purple or yellow flowers. One of 3 treatments is to be applied to each plant tray: a control, which is plain water, a commercial flower food, or a new and untested flower food. The plant trays will be stored in 4 separate glass houses, 6 plant trays per glass house. Using Genstat, we can create the design as follows. From the menu, select Stats, Design. Generate a standard design. To produce a randomized complete block design with our 2 treatment factors, flower food and flower type, I've selected two-way design in randomized blocks from the drop-down list here. I've used the 4 glass houses as our blocking structure, as we can't guarantee the glass house conditions are perfectly uniform. There may be variability due to light and shade or temperature. The plant trays are our experimental units. The different flower foods and the control make up the 3 levels of treatment factor 1. Lastly, the purple and yellow flower types make up the 2 levels of treatment factor 2. This gives us our number of experimental units, which are 24 plant trays, and we'll let Genstat randomize the design for us. I've selected the Display Design in a Spreadsheet checkbox so that Genstat will produce a spreadsheet of the design. The Randomization Seed field allows you to specify a seed used to randomize the design. Genstat automatically changes the seed every time a design is produced. However, you can supply your own seed if you want, and keeping the same seed will generate an identical design. If you're following along in Genstat and want to produce an identical design to the video, set the randomization seed to the same number shown here. I'll click Run, And here's our spreadsheet and output. The output shows a basic schematic of the design. The blocking structure, glasshouse, is shown across the top, with the plant trays on the left. The treatment factors are shown as groups of 2 numbers, and this description tells you what order they are in. Flower food is the first number, and flower type is the second number. Looking down the first column, this reads, in glasshouse 1, position the first plant tray. Apply flower food 1 to flower type 2. The second entry reads, in glasshouse 1, position the second plant tray. Apply flower food 2 to flower type 1. Underneath the design schematic is a skeleton analysis of variance table giving the degrees of freedom of the treatment factors and the structure of the strata in the design. The treatment effects are estimated in the glasshouse dot plant tray stratum, which represents the variation within the glasshouses. The glasshouse stratum represents the variation between glasshouses. The spreadsheet presents the design instructions in a similar way, but you can edit the labels if you want to make them more meaningful. The Check Power button becomes active once you've generated a design. This allows you to calculate the power of your design. That is, for a given level of response between 2 treatment means and a given significance level, Genstat will calculate the probability of detecting this response. To calculate the power, Genstat needs to know which treatment term you want to calculate the power for and the size of the difference you want to detect. Let's say we want to detect differences as small as 2 days in the mean number of days flowers last between the different flower food by flower type treatment combinations. You also need to indicate how large you expect the residual mean square to be for the stratum that contains the selected treatment term, in our example, the glasshouse dot plant tray stratum. Let's assume this is 0.5, however in practice, this should be obtained from an earlier analysis of similar data. The other options allow you to set the significance level and the type of test, calculate the power of a specified contrast between means, and control the printed output. You can find out more about these options in the help. When I click OK, a dialog box pops up telling us that the power of our design is 0.962. The Replications Required button allows you to calculate the number of replicates required for a design to detect a given level of response between 2 treatment means at a specified power and significance level. For a randomized block design, the replication depends on the number of blocks, in our example, glasshouses. Let's see if we could consider running the experiment with fewer glasshouses. To make the calculation, Genstat needs to know which treatment term you are concerned about, the significance level, the power, the size of the difference you want to detect, the within block variance, i.e. residual mean square of the glasshouse dot plant tray stratum, and the type of test. We'll leave the power and significance level at their defaults. When I click OK, a dialog box pops up giving the required number of replicates. In this example, we could reduce the number of glasshouses from 4 to 3 without seriously undermining the power of the experiment. If we click Apply, the number of blocks in the design menu will update to 3. However, if we click Cancel, the pop-up will simply close. Clicking Change will return us to the Replications Required dialog. In the output, along with a report of the replications required, a table gives the power and the standard errors of differences, etc. for different numbers of replicates. Notice that from this table we can also see that the power of our current design with 4 glass houses is 0.962. Let's now explore a different type of design. A field trial is being set up to investigate the effects of applying 4 different levels of nitrogen fertilizer to 3 varieties of oats. Due to practical reasons, the oat varieties can only be sown over large areas of land. However, the fertilizer can be applied to smaller plots. A split plot seems to be a suitable design. The field is first partitioned into 6 blocks. The blocks are then split into 3 whole plots. The 3 oat varieties will be sown over the large whole plots. The whole plots are further split into 4 subplots. The 4 nitrogen levels will be applied to the smaller subplots. Here's how we generate this split plot design. If you're following along in Genstat and want to produce an identical design to the video, set the randomization seed to the same number shown here. I've selected Split Plot Design from the drop-down list. The large field area is split into 6 blocks. The whole plots and subplots are named appropriately. The 3 levels of oat variety will be applied to the whole plots. Lastly, the 4 levels of nitrogen will be applied to the subplots. This gives us our number of experimental units, which are the 72 subplots. We'll let Genstat randomize the design for us and select the Display Design in a Spreadsheet checkbox so that Genstat will produce a spreadsheet of the design. Now click Run to produce the spreadsheet and output. The output shows a basic schematic of the design. The field blocks are shown on the left with the whole plots just to the right. Here are the smaller subplots within each whole plot. The treatment factors are shown as groups of 2 numbers, and this description tells you what order they are in. Oat variety is the first number and nitrogen level is the second number. Looking across the first row, this reads, in block 1, whole plot 1, sow oat variety 3 across the whole plot. In subplot 1, apply nitrogen level 1. In subplot 2, apply nitrogen level 2. In subplot 3, apply nitrogen level 3, and subplot 4, apply nitrogen level 4. In whole plot 2, you're instructed to sow oat variety 1 across the whole plot. Then, in subplot 1, apply nitrogen level 4. Subplot 2, nitrogen level 3, subplot 3, nitrogen level 2, and subplot 4, nitrogen level 1. Again, the spreadsheet presents the design instructions in a similar way. If you want to learn more about the design of experiments using real-world examples, we recommend this book. You can also read through Chapter 6 of A Guide to ANOVA and Design in Genstat, which is available from the Help menu.